Okay, so guys, today what we're going to do is we're going to do what Bohr did. We are now going to connect light with electrons with structure. To do this, what we've got to do is we've got to first of all talk about how is it that Bohr interacted with light. And then once we understand how Bohr collected and interacted with light, what we can then do is talk about how does that give us information about the electron structure of atoms, and then we'll actually start fiddling around with this and make some real measurements, if you will, and figure out how this all fits together. So guys, first of all, as we get into this, we need to talk about what are called electromagnetic spectra. So when we talk about electromagnetic spectra, we understand, guys, that visible light is actually a mushing together of many different wavelengths of light. Guys, here on Earth, we do not, well, probably nowhere, do we ever experience pure, what is called monochromatic light. Yes, that is the only place where monochromatic light can be experienced. For example, if you look on the back of my little laser pointer right here, right there. Caution, laser radiation, wavelength 532 nanometers. Now guys, if we were to look on that spectra that we looked at last time in class, we would find out, looking at the ceiling, that 532 nanometers lies right in the middle of green. So guys, this is in fact monochromatic light. The light that is coming off of this laser is only 532 nanometer light. But guys, that's where it stops. If we look at Carson's sweatshirt and we understand that it's red, we would understand that oh, maybe we should do this. Would that red light be longer or shorter wavelength than 532 nanometers? Longer, because it's lower energy, it's redder light. But guys, we couldn't say that that's 600 nanometer light, and even if some of it was 600 nanometer light, it would actually be a blending together of a lot of different wavelengths of light that our eyes then absorb and then send to our brain this message that says, hey, this is red. But guys, understand that when we experience colors other than lasers, what we're actually seeing is a blending together of a lot of different individual wavelengths. And so when we talk about these, we can then separate them into what are called spectrum. And guys, there are three types of spectrum: continuous spectrum, absorption spectrum, and emission spectrum. And I'll draw the distinction in them in just a minute, but let's check continuous off the list first of all. So guys, a continuous spectrum is all the colors of light that exist in our visible spectrum. So guys, a continuous spectrum goes from red to Roy G. Biv violet, the whole spectrum of light. Now guys, how do we experience full spectrum continuous light? What does that look like to us? White. Guys, our brains understand all of the colors together to be white. You may want to write that down next to continuous. When we experience white, guys, there's no such thing as the color white. There's red, orange, yellow, green, blue, indigo, and violet, but white is a purely human experience. There is no white light. Our brains understand the color white to be a combining together of all of the colors of the rainbow. Are you just scratching? Yeah, go ahead.
Is that why lasers are for our eyes?
Yeah, but that said, I mean, you've all had the experience of doing the self-check at Walmart, right? And you scan the thing through and you're lined up just right, and that red laser bops you in the eye. I mean, lasers necessarily are not harmful until their wattage is high enough. So even in that, and wattage is a function of the number of photons. So, I mean, yeah, you certainly wouldn't want to, but you'd probably be okay. But there's a threshold there where the energy that's being transferred to your eye as multiples of photons is actually enough that it causes damage. And that's more the case with laser light because it's such a focused, concentrated source of energy. So just a second, go ahead, Gavin.
So if I'm right, black is the absence of all colors, correct?
Black is the absence of light. Yes.
So does that mean that your shit's not emitting a wavelength?
So the difference, I don't want to get into this a lot, but the difference that we have to understand is there's a difference between emission and reflection. Okay, so my shirt is not emitting light. What it is actually doing is taking the white light from, let's say the light bulb is the only source of light in the room. It's taking the white light from the light bulbs and it is absorbing all of these wavelengths and re-radiating. If this was purely black, it would not be radiating any energy. That's why black clothing in the sun gets so hot, because it's not reflecting any energy, it's absorbing all of it. And conversely, that's why white clothing tends to be cooler, because it's reflecting more light than it's absorbing. So that's the difference there. Understand though that even black is not purely black. It's actually re-radiating some wavelengths at very low energies. Go ahead. Yeah, if you were trying to do it mathematically, you would have to go through and figure, because even when we, and you'll see this in lab when we do this after fall break, we're going to take the white light from these light bulbs and actually break it up into its prism, its spectrum, and you're going to find out that that's actually truly not all the colors of the rainbow. It's actually 7 or 8 different colors spread across the spectrum that's enough to trick our brain into thinking white. But we could actually find each of those 7 spectrum added up and get the light, get the energy. Exactly. But if we were actually doing full spectrum light, which is sunlight, sunlight does in fact carry all the colors of the rainbow, then we could do it, rather than doing it computationally, we can do it just by getting a meter that measures energy transferred by light. So yeah. I don't know. Yeah, and frankly, I don't know. I'm not sure. Certainly they're skewed, right, towards certain colors, but I don't know if those are prominent bands or the only bands. I really don't know. Okay, so guys, as we dig into this then, let's talk about the one that we're going to talk about. These are what are called emission spectra. So here's the idea. When we take a gas and when we excite the molecules in a gas, by passing high voltages through them, we get these electrons to jump into higher energy levels. Then, guys, we can take the light that is emitted by these and break them down into an emission spectra by passing them through a prism. I'll show you an example in a minute, but when we do that, what we get are lines of color separated by black spaces that represent the missing wavelengths. So guys, what I'd like to do is show you pictures and help you understand the difference here. Can we do pictures? You ready? Joe, you okay? Yeah. Okay, so guys, pictures go like this. There's one thing that I don't like about this, but we can get over it. I wish that weren't a light bulb. What should it be to get a continuous spectrum? It should be the sun. There may actually be some truly full spectrum light bulbs, but I'm not familiar with them. Again, typically if you pass light bulb light through a spectrum, you actually see something that looks more like this. Guys, this is where we are going to spend our time in this class. So this is the idea. If you take a gas and you heat it up, or in our case, what we'll do is pass a current through it, what happens is we get electrons that move from ground states out to excited states. When they fall from the excited state down to the ground state, they release energy. Now, what types of energy are associated with short falls? What will that look like? Red or light. And then if we have electrons that are going through longer falls, we will end up with light shifted towards the blue and the violet. So when we take this light that's coming off of our excited atoms and pass it through a prism, we would find out that in fact it's actually only composed of a few bands of energy. So the question is, why? What do each one of these bands represent? Exactly. A different electron fall. So the red colors are short falls, the violet colors are longer falls. And so the idea, and this is what Bohr did, is he realized that if he could not just say that this is a short fall, but if he could figure out if it was a fall from where and to where, he could then map that backwards and figure out the electron structure of the atom. Now guys, there's one other point we need to make before we try to entertain questions, and it's this. What do these black spaces represent? Places where electrons cannot be. Think about that. Mull that over for a minute. These black spaces represent places that electrons either cannot be or cannot fall to, which is really the same thing. So the idea here, guys, is this. If electrons could be anywhere they wanted to be around the nucleus of an atom, all atoms would emit continuous spectra. Because if the electrons could be anywhere, and if they could fall to anywhere, then they could release all potential wavelengths of light. But that's not what Bohr found. Bohr found that there are some places electrons can be and some places electrons can't be. And because that is true, some falls are possible and some falls are not possible. And consequently, the emission spectra that we see have gaps in them representing the places electrons can't go or can't fall back to. You get the idea? That was the magic of the work that Bohr did. See, prior to this, all that we had was Rutherford's nuclear atom, right? And in Rutherford's nuclear atom, they thought the electrons could be anywhere. And if the electrons can be anywhere, then all of their spectra would be continuous. When Bohr found that these spectra were not continuous, and instead they had gaps, it was Bohr that took that and said, well, then clearly that means the electrons have places they can be and places they can't be. You get the idea? So guys, what questions do you have then specific to this idea? Yeah.
So red is short because it's short falls.
Yes, exactly. Yeah, and so it's kind of like the analogy that with sound where we said it was loud. Like if I fall a short distance, it's quiet. If I fall a longer distance, it's louder. With light, if you fall a long distance, it's bluer, and shorter distances are redder because it's lower energy light. Is that okay? Yeah. Let's go this way. Go ahead, Jared.
So like when you excite the electrons, do they all go to the same one and then they like drop into the
No, and that's the thing that's interesting about this. So let's use our sound analogy really quickly. So the idea is that say that it takes, I'm going to just make up a number, 10 joules of energy to move me up here. Okay, so what happens if you add 10 joules of energy to me? I jump up here. What happens when I fall down? I release 10 joules of energy. Now, what if you add 8 joules of energy to me? What happens? Nothing. Because I can't hover between the rungs, it's not like you add 8 joules of energy to me and I get energized, but not energized enough to step up a rung. So the idea is either I can absorb 10 or I do nothing. And so the idea is that relative to your question, not all electrons excite to the same place because some electrons will receive less energy. So say that, for example, you're in your ground state down here, and I know this isn't a great picture, but some of these, here, let's do it on the board. So if we have energy levels, so here's the nucleus and here's our energy levels, and if it's 10 joules between here, and if it's 5 joules between here, some electrons will absorb the 10 joules and go to there. Some of them will absorb the 15 joules and go to there. So not all electrons absorb the same energy, therefore not all of them promote to the same energy levels. But it has to be 10 or 15 or nothing's going to happen. Go ahead, Jared. Not necessarily, yeah, and that's one of the things we're going to talk about in PES next time, because that's all that PES is doing is, well, adding so much energy that they don't just jump up, they jump out. But we'll talk more about that later. Parker? You can't. Yeah, you can't. Yeah, so if you were to take that atom and if you were to hit it with a 12 joule photon, nothing would happen. Yeah. Well, and that's the thing. Until you figure out how much energy is associated with energy level infinity. And that's what we're going to talk about today. Because if you can add enough energy to get this thing to go to energy level infinity, now the electron's gone. And we call that ionization energy. So you can add 10 joules, 15 joules, or enough energy to make the electron go completely away. Those are the only things that can happen in this model. Is that okay? Yeah?
But you still could add more energy just with food, right?
But have you really then added it? Because what would happen is the energy would just pass through as if it had never been absorbed at all. Yeah, yeah. No, 12 would not do anything at all. And that was the thing that was really shocking to Bohr, was that either it's almost as if this electron is sitting here looking out into the distance and going, hey, there's a rung 10 joules away, and there's a rung 15 joules away, and if you only give me 12 joules, 8 joules, I'm not even going to try because I know I can't get there. It doesn't absorb it and re-radiate it. It doesn't absorb it at all. Yeah, go ahead. Well, and that's what we're talking about up here. So again, the things that can happen is they can either promote to these energy levels that are possible, or if you add so much energy, you can blast the electron past this theoretical energy level infinity, and then it just goes away. And we call that amount of energy ionization energy. Yeah, go ahead. Yeah. Yeah.
Like in between them, there aren't supposed to be electrons. There's like special
Because, yeah, it's just the way they did the rep. No, don't read anything into that. I don't know why they did that. It's a good question, though. Go ahead.
Is there a way to make them go the other way?
Make them fall? No, because understand that these electrons, by definition, are in their ground states. They're as low as they can go. So all of the other, and so if you've got say you've got an electron in the third energy level, in its ground state, the reason that that third energy level is its ground state is because everything inside of it's full. So these electrons will all naturally fall to their lowest energy levels. And so all we can do is promote them up and then allow them to fall back down. We can't push them any deeper because it's full. Does that make sense? Is that what you were asking?
Yeah.
Okay, yeah. So someone else, we're good. Go ahead, Josh.
So when the emission spectrum
Yes.
Because not all of them get the same amount of energy we get is just up, right? So would we see a statistical like brightness as we go further up because it's less likely that they will get enough energy to become like a violet emission as much as like a red emission. So it would get darker.
I don't know. I'm not sure.
The other question C connected. So we keep applying this concept in a very Bohr like form of how would we apply this, like knowing how the orbitals actually look like?
Yeah.
Is it going from like a 1s to a 2s?
No, and Josh, that's a really good question. Let's answer that. So this is cool. So Josh is saying, wait a minute, we're applying these ideas in a Bohr sense, right? So now let's see if I'm good enough with a laser to do this with Schrodinger. So here's the idea. Did you understand Josh's thought? That we're talking about all this stuff with emission with Bohr, but we know that Bohr's not right. Here's the answer. When Bohr first started doing this stuff, he would say that we have an electron that's here and it falls down and it releases energy. But here's what Bohr started to find. Well, you know what? Let me do it up here. This would be better, I think, if I had an eraser. So let me sort of redraw this without the lines. So he found, here's the nucleus, here's our energy levels, and let's just say that we have an electron that goes from 3 to 1. Now let's do 2 to 1. That'll be easier. So we have an electron that falls from 2 to 1 and it releases energy. So that's the Bohr model. But here's what he found. All of the electrons that fall from 2 to 1 don't have exactly the same amount of energy. What he found, and this is a short fall, so it would be red light, what he found is that there were some electrons that had slightly lower energy light, and there were other electrons that had slightly higher energy light. So within this band of energy that was being released, that was clearly from energy level 2 down to energy level 1, there were some of them that were slightly lower energy and some of them that were slightly higher energy. Do you want to guess how many there were of each? 2 of these and 6 of these. Why? Because these are the 2s and those are the 2p. So what they found out as they started doing this emission spectra stuff with better and better instruments is that all of the electrons that were going from 2 to 1 didn't have exactly the same energy. Some of them were slightly lower, some of them were slightly higher, and that was the supporting evidence for the sublevels. And that's where we talk about PES. And we'll get into that in just a minute. We'll get into that next time.
And also, if it's going up to an electrical orbital, what happens if the electricity goes up to already off, right?
It can't. Yeah.
So that means that the valence electrons are going to the midlight.
Not necessarily because they're all moving at once. But also understand that when Bohr was doing this work, it was with a hydrogen atom. And guys, this is critical. When you go to look at the homework today, you are going to see in your homework, it says very specifically, the emission spectra of a hydrogen atom shows this. And you're going to be thinking to yourself, wait, all a hydrogen atom has is a 1s electron. But guys, understand that even in a hydrogen atom, there can be 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5. All of those are possible. And so when they originally did this work to show the energy levels and the sublevels, it was with hydrogen atoms promoting into energy levels that we don't even think of as existing. So that's the thought there. So guys, hold on. Are you okay with spectra? I know this is fascinating, but we also have a lot of stuff we need to do. Are there questions that will bring clarification that will allow you to better move forward? Go ahead. Yeah.
So why would, if you have 14 tools in it, why would some of them not go?
Because it's not exactly enough. Because if you look at the... So, say that this is 10 and this is 15. If you give me 14, I can't hover right there. Therefore, I don't do anything at all. It's not like I can go past it and then fall back to the chair. Either I go here or I go there or I do nothing at all. It has to be the exact number unless we add so much energy that it blasts it completely out of the atom. Okay, so guys, we're going to go on. I think you have a sense of this. So let's talk then about how we come up with these numbers. So guys, where do we get the 10 and the 15? You ready? It goes like this. So and I don't know that you necessarily need to write this down. This is a transitional thought. So guys, you understand that the bands in an emission spectra correspond with the energies that these electrons release as they fall. So what we can do now is we can connect these bands with electron structures. But we can only do that if we can quantify the energies of each energy level. So here's how this goes. We can calculate the energies of the energy levels. We can come up with the 10 and the 15 using a very simple equation. Please don't write this down, just watch. So guys, it goes like this. That is the equation. This guy in the upper left-hand corner is the equation that we use to calculate the energy of an energy level. So what are the variables? Well, guys, n is the principal quantum number. Energy level 1, energy level 2, energy level 3, energy level 4, and so on. So guys, this then means that the energy of an energy level is equal to the negative of something called R sub h. You'll find out later it's called the Rydberg constant, divided by n squared. So what does that mean? Well, first of all, the value for R sub h. It's 100 joules. Now, let's look at an atom. So here's an atom up to the 5th energy level. Now, guys, what we're going to do is we are going to figure out the energies of each of these energy levels. So do the math with me. What is the energy of the first energy level? Well, plug 1 in for n. What is 1 squared? 1. And this is negative R sub h, so the energy of that would be negative 100 joules. Please don't write this down. You get the idea? Now, guys, let's do the second energy level. Plug in 2 for n. What's the value for energy? Negative 25. So it's negative 100 divided by 2 squared is negative 25. That was one click too many, but we can do the math. So if we plug in 3, 3 squared is 9. Negative 100 divided by 9 is functionally negative 10. It's really negative 11, but let's round. You okay? Now, what about energy level 4? Plug in 4 there. 4 squared is 16. Negative 100 divided by 16 is functionally negative 6. Now, guys, what about energy level 5? What is the energy of energy level 5? Negative 4. So the energy there would be negative 4. You get it? Now, hold on. We're not doing questions yet. Let's talk. So guys, now we need to talk about how this all fits together. So the first thing we need to do, maybe we should bring the lights up in case you need to jot thoughts down. Don't draw the picture. But guys, this is the idea. What happens, we're going to talk about this qualitatively first. What is happening to the energy of these energy levels as you move from the middle to the outside? Is the value of the energy for these energy levels going up or down? Up. This is negative 100. This is negative 25. What number's bigger? Negative 25. This is negative 10, negative 6, negative 4. So as we move out from the nucleus, the energy of the energy levels is going up. Now, guys, you should have a fundamental problem with these numbers, though. What on stinking earth is negative energy? It's like negative mass. We're not talking about a change. We're not saying losing 10 pounds. We're saying this thing weighs negative 10 pounds. Similarly, in energy, we are saying that these energy levels have negative energies. How do we understand negative energies? Now, guys, let's think about this. Let's think about an electron in, let's just say, the second energy. Oh, boy. So we've got an electron in the second energy level. What is the energy of that electron? Negative 25 joules. So we understand the 25 joules part of it. That's the amount of energy it has. What does it mean that it's negative? And it's not the charge. We understand electrons are negative, but that's not the answer. So how do we understand it? Guys, think about it this way. What is it that gives this electron energy in the first place? Why does that electron have energy in the first place? Because what? It's the attraction to the nucleus. In the same way, guys, potential energy, right? We have energy because we're attracted to the center of the earth. Similarly, electrons have energy only due to position. Their attraction to the nucleus. And so, guys, if you can wrap your head around that idea, because that energy is imparted by something else, we understand that it's negative because we're thinking of it as an attraction to that nucleus. And so because we understand that it's an energy of position due to attraction, and that energy is imparted by something else, maybe then we can wrap our mind around the idea that it's negative because it's relative to the thing that's imparting the energy to it. And this makes more sense if you carry it out to the extreme, and then I'll give you another analogy. So guys, what do we have to do to get the electron to jump up to there? Add energy, right? How much? 15 joules. Add another 4 joules. Add another 2 joules. What if we keep adding energy? The electron is going to continue to jump up and up and up until eventually what happens to that electron? It's gone. And what do we call it when that electron is gone? Ionization energy. So guys, the definition of ionization energy is the amount of energy that we need to break the association with the nucleus. How much energy is that? Well, that is the energy at energy level infinity. So when we add enough energy that electron has been fully removed from the nucleus, we've now broken the association with the nucleus. Now think about this. When we add energy to, this is cool. When we add energy to the atom, we always understand that energy to be positive, right? But what is that energy doing? It's breaking the association with the nucleus. So if we're adding positive energy to an electron to break the association, that associative energy has got to be the opposite for the addition of energy to undo it. And that's why we make it negative. So guys, whether you wrap your arms around this or not, fundamentally you've got to understand that the energy of an electron is negative. This you should put in your notes. The energy of an electron is negative to a maximum of what? This is sad. What is the most energy an electron can hope to have? 0. So guys, the most energy that an electron, and understand we're not talking about charge, they're still negative. But the most energy that an electron can hope to have is 0 energy, which tells us what has happened to the electron. It's no longer associated with the nucleus, it's gone. And how much energy does it take to get this electron to 0 energy? What do we call that amount of energy? Ionization energy. Now, hold on. There's another analogy that I've heard that I don't mind, but I don't like opening with it. But guys, it's not bad. Think about it like this. Imagine that this is the center of the earth and that this is the surface of the earth. That makes this a hole. Now do the negative energies make sense? That if you're in a hole in the earth, the most elevation that you can hope for is 0, because that's the surface of the earth. So if this is your 0 point, the point where you're at the surface of the earth, then all of these elevations are understood to be negative because they're relative to your 0 point, which is the surface. Similarly with electrons, if you understand that this is where there is 0 attraction, anything beneath 0 has got to be negative. It's not bad. But however you wrap your head around this, guys, you've got to understand that this energy is an energy of attraction. That attraction becomes 0 at energy level infinity, and that's when the electron's been removed, the attraction's been broken, and we call that ionization energy. So guys, let's ask pertinent questions. Go ahead. Good. And you know what? It's an important distinction. You understand that electrons have kinetic energy because they're moving. The energy that we're talking about here is potential energy. In the same way, because remember, potential energy is the energy of position, the classical definition, like gravity. In the same way as gravity, this is positional energy. Yeah, that's a very important distinction. Go ahead.
So, do we just make the values negative so that we can have a nice placeholder?
You can think of it that way. We make the values negative so the math works out. So when we're adding energy to the electrons, moving them out, we understand that they're moving out to higher energy levels, but because we're adding positive, it only makes sense if those are negative, to a maximum of 0.
Okay, so they actually have potential energy, but
We just changed the sign. And I'm totally comfortable with you understanding it that way. The negative just gives us a positional reference relative to the fact that out here the energy is 0 because there's no attraction. Yeah. Anything else? Yeah. It's given to us. Yeah, it's a constant. It's called the Rydberg constant, and it truly is a constant. Okay, go ahead. It does. So this is the Rydberg constant only for hydrogen, and that's the only way that we will ever solve these. Yeah. You guys okay? Oh, go ahead.
So, like, with the example of 10 joules that you had, if you had, like, 20, would that be, like, 2 electrons jumped up to 10?
Let's do that now. Okay, so this then is the idea. Say, guys, that we've got an electron right here in energy level 1, and we kick that electron up here. Is that 4? 2, 3, 4. So we kick that electron up to energy level 4. How much energy does that require to go from here to here? 94 joules of energy. Now, guys, the tricky part is trying to do this math. It gets really weird when you're dealing with signs. So what we've got to do is change in energy is equal to energy final minus energy initial. And signs are critical. I would encourage you to do this with me. This is all sort of hypothetical, but you've got to understand the math. So the question is, how much energy goes into the electron to go from energy level 1 up to energy level 4? It's critical that we get the signs right and the final minus initial right. So the change in energy, our final position is -6 joules minus our initial position, which is -100 joules. Now when we do the math, -6 minus a -100 gives us what? +94 joules. So the 94 is the amount of energy that we needed to add. What does the positive tell us? What does the positive tell us? It's gone in, right? In order to get an electron to move to an excited state, we have to add energy. Now, given the math, we can show that that's a positive amount. You can think of it as being endothermic, but it's not thermal energy. But the idea is that the positive told us that it went in. Now, guys, what if we took that same electron and went from 4 to 1? How much energy is going to come out? Also 94 joules, but now what would the math look like? Well, the math would now be the opposite. Our final position is negative 100. Our initial position is negative 6. And now this is negative 94 joules. And the negative tells us it's been radiated. If this next test doesn't go well for you, this is likely going to be the reason why. You're getting sloppy with signs. Guys, it's critical that you get the signage right on this. You've got to be really, really careful with this. So now, Jared, one of the two, you asked a question about what if you added twice or something like that? Yeah, so let's pick something that's a little more even. So say that we went from 2 to 3, right? So that's a 15 joule difference, right? So what if we added a photon that added 30 joules? The answer is nothing. Photons can't split energy. So if we add a 30 joule photon to this, it will not promote 2 electrons. It will do nothing. So it's 1 photon per electron and the energy can't divide. Okay, did that answer your question? Okay, so guys, are you comfortable with the concepts and the math? You're good? You're sure? Okay, now guys, oh, go ahead.
So 100 joules is probably correct.
No, because it's actually not 100 joules. I made that up. So guys, grab your AP equation sheet. Really, guys, grab your AP equation sheet. With the revision of the test, they wrote this equation out of the test, out of the equation sheet. They can still have you solve this equation, but they will give you the equation in the test. I don't know why they drew the distinction, so let's put it on our equation sheet. Guys, here's the equation. Write it on your equation sheet under the electrochem, or under the atomic structure part. I would even encourage you to write this as a more formal equation where it's E sub n is equal to negative R sub h divided by n squared. But guys, here's the trick. Oh gosh, thank you. Like so. But guys, here's the trick. R sub h is not 100. R sub h is 2.18 times 10 to the negative 18th. I made up the 100 because it's easier to think about numbers that make sense in our world, like 100. Guys, 2.18 times 10 to the negative 18th is such a nonsensically small number that to try to teach you the concepts, you guys would have been so cramped up over the negative exponent that your brains would have exploded. So all you've got to do is take the same thing that you understand and plug in a different value for R sub h. Now guys, listen, is this number positive or negative? It's positive. When you plug it in here, it becomes negative, just like 100 is positive. Maybe I should have wrote it as 1 times 10 to the second. But guys, it's still a positive number. It's smaller than 1, but not smaller than 0. It's still a positive number, but when we put the negative in front of it, because it's negative R sub h, now it becomes negative, coming back to the idea that all the energies of the energy levels are always negative. You guys good? Okay, so let's answer a couple questions, solve a problem, and call it a day. So guys, first of all, notice, as you already know, that this produces all negative energy level values. So what happens as n goes up? Well, as n goes up, the radius increases, right? These things get bigger. In addition, the energy increases by becoming less negative. And then finally, as we said, when n reaches infinity, what happens to the electron? It's gone. What is its energy? 0. So guys, let you catch up. We are going to solve one problem relative to this. And then we're going to call it a day. This is going to be the full circle thing. Yeah. What does that mean? It's the energy of an energy level. So it could be E sub 1, E sub 2, E sub 3. But we would call it the energy of an energy level. Spencer, did you have a thought?
So the reason that numbers have to be negative is not because like they have negative energy like in this weird thing, but it's because we know that the n negative, the n infinity is 0.
Correct. And because that fixed point, when E sub n is infinity, the energy is 0, given that fixed point, everything has to be negative because our maximum is 0.
I just don't quite understand what negative energy is quite yet.
Well, I mean, we understand what negative energy is as much as we need to. We understand that it's referential.
Okay.
And it's referenced to that 0 point, which is when the energy is at a maximum. So if the maximum amount of energy is 0, any other energies by definition have to be negative because you can't have more than the maximum. You guys okay? All right, so guys, let's solve this. Here's the deal. Don't write this down. So here's the connection. By knowing the energies then of the energy levels, we can now figure out what these electrons are doing when they fall and release light. For example, we have an electron that's going from the 4th energy level down to the 2nd energy level. What wavelength of light will be released when that happens? Guys, this is a multi-part calculation where one thing leads to another leads to another. So let's talk about it, and then we'll turn you loose and let you solve it. So here's our nucleus. And then we've got energy levels 1, 2, 3, and 4. So we've got an electron going from 4 down to 2. So how can we figure out the wavelength of that light? What do we need to know? The energy of 4 and the energy of 2. Then what are we going to do? Change in energy is equal to final minus initial. That will then give us the change in energy, which is the energy of the photon. What are we then going to do with the energy of that photon? E equals h nu. That will give us what? The frequency. And then we can take that frequency and convert it to wavelength. How? C is equal to lambda nu. Give it a shot. Everything will assume that it's hydrogen. We have no ability to solve it if it's not. Oh, it's 2... Yeah, guys, make sure you get this in your sheet. It's 2.18 times 10 to the negative 18th joules. So guys, again, energy level 4 to energy level 2. So your goal is wavelength. The end game is what is the wavelength of light that's released when it goes 4 to 2? 4 to 2.
So the bottom part of En equals negative RH over N2. Is N2 at the bottom, is that a change in N2? Or?
No, so it's n squared, where in this case n would be 4 and n would be 2. You've got to solve it twice. It's not a change. I mean, I guess technically you could make it a change if you want to try to derive an equation by solving it twice and then subtracting. That's what your book does. I don't know if you saw that, but your book actually does take that equation and turn it into a change in energy equation by plugging it in twice and then rearranging it. So guys, I'm going to do a little bit of the legwork while you guys are fiddling around with this. So E sub n is equal to negative R sub h divided by n squared is equal to negative 2.18 times 10 to the negative 18th joules divided by 2 squared and negative 2.18 times 10 to the negative 18th joules divided by 4 squared. Two point 18 and 10 to the negative 18th. You're probably beginning to get a sense of why it is I started with the number 100. Oops. So guys, can you confirm or refute these numbers? I got the second energy level at negative 5.45 times 10 to the negative 19th joules. Am I okay? And then I got the fourth energy level at negative 1.36 times 10 to the negative 19th joules. Am I okay?
Yeah.
Okay. Then we're going to go change in energy. This is the part you're going to screw up on the test, is energy final minus energy initial, being very careful of signs. We are going from 4 to 2, so our final is negative 5.45 times 10 to the negative 19th joules minus a negative initial, which is negative 1.36 times 10 to the negative 19th joules. Now guys, when I do this math, what should the answer come out to be? Positive or negative? Why negative? The electron is falling, so energy is being released. It's a very important error check. So 5.45 times 10 to the negative 19th, and that is negative, and then we're going to add to that 1.36 times 10 to the negative 19th, and sure enough, I get negative 4.09 times 10 to the negative 19th joules. Can you confirm or refute that? Am I okay? Okay, guys, now what are we going to do with this? Energy is equal to h nu, or you can do that, but I'm not going to. So Planck's constant is 6.626 times 10 to the negative 34th joule seconds. Oh, I got to sneak that in there. Uh-oh. Negative 4.09 times 10 to the negative 19th joules. So this number divided by 6.626 times 10 to the negative 34th, and we get negative 6.17 times 10 to the 14th hertz. Now guys, what are we going to do with the negative at this point? This is the point where I like to drop it off, because that negative sign simply means emitted. At this point, we understand that we're dealing with emitted light. We just need to know its frequency. So when I come over here to C is equal to lambda nu, or 3 times 10 to the 8th is equal to lambda times 6.17 times 10 to the 14th hertz, it's at that point I just drop it. So 3 times 10 to the 8th divided by 6.17 times 10 to the 14th, and I get 4.86 times 10 to the negative 7th meters. Go ahead.
If we, so like, I forgot the sign.
Yeah.
So like, could we calculate the signal with no signs, and then at that point, possible signs, is it going to factor up, and then it's
Are you talking about in this region?
yes. So like, when you get a 6.17,
Oh, down here? Yeah, but understand that this has got to be negative. And I would not be comfortable artificially making these positive. My suggestion to you would be, rather than playing with signs, just be careful and do it right. Yeah. For this one?
no, because the first one, yeah, because so it's the Rayburn constant.
So were you getting a negative of a negative? Because understand, the Rayburn constant in and of itself is positive. We're just adding the negative from the equation. So I'm confident in my numbers, and frankly, I'm not good with the TI calculator. So no, that's what I'm saying. What I'm suggesting is I'm not much help to Everett, because I don't know why his calculator's not cooperating. So, hey guys, let me ask you one question though before we depart from this. What is the wavelength of this energy in nanometers? 486 nanometers. Because guys, remember, nanometers are 10 to the negative 9th. So when you see these wavelengths that tend to be visible light range 10 to the negative 7th, understand that that is the same as 486 nanometers, where we're 10 to the negative 9th. On the AP test, they like to do that. They'll ask you, what is the wavelength in nanometers? Understanding that is not in nanometers, you've got to move the decimal place 2 spots. So be careful in units in these particular problems. So any questions? Okay, here's your homework gang. Stay put. Actually, I'm going to stop recording for just a moment.